I just wanted to say a few words about the USACM Energy and Earth System Technical Thrust Area and give a couple of announcements about some of our upcoming activities. So I'm Irina Tazar. I'm the chair of the Technical Thrust Area. We cover a wide range of topics, some of which are listed here. So from climate to Earth system modeling to geomechanics, wind, solar, nuclear energy, carbon sequestration, capture and storage, oil, gas recovery. Um, so we have these webinars that where we sort of have different topics each time. So hopefully, if you're not interested in one topic, maybe the following month we'll have something that you are interested in. I would encourage you to join the Technical Thrust Area. It's free for USACM members. You could also follow our LinkedIn page if you're interested in just hearing updates on activities that doesn't require a membership. Let's see, for USACM. So we do have this is our last our last presentation webinar of the year. We do have kind of a mostly full program for next year. So our next speaker will be Professor Artyom Korobenko from University of Calgary on January 28th. So hopefully I'll see some of you folks next year at some of these webinars. The other thing I wanted to announce is that we are organizing our first thematic workshop in September 2025. Some of you may have remember voting. So we had to let people submit ideas for topics they were interested in and then vote on the ideas. So ultimately, the winner was kind of like a merging of two ideas that had been submitted. So it will be artificial intelligence and digital twins for Earth systems. It will take place at UT Austin in Austin, Texas. Right now, we're still kind of finalizing the dates, but most likely it'll be September 22nd through the 24th. And once the website is live and all the information is available, I'll be sure to share that using our listserv and LinkedIn and stuff like that. So, okay, so let's hand it over to Todd here. Okay, so it's really a pleasure to introduce our speaker today, Professor Todd Griffith from University of Texas at Dallas. So Professor Griffith is a professor of mechanical engineering at UT Dallas, where he leads a research group that focuses on developing new technology solutions in wind turbine design and structural dynamics. He's been at UT Dallas since fall of 2017, and prior to that, he was actually a principal member of the technical staff here at Sandia National Laboratories, which is where I currently work. There he was a technical lead for Sandia's offshore wind and energy program, responsible for developing and leading national projects for the U.S. Department of Energy. He completed his PhD work at Texas A&M in aerospace engineering and bachelor's and master's degrees in mechanical engineering from the University of Kentucky. And he is the co-founder and deputy director of the UT Dallas Center for Wind Energy. So I'll go ahead and hand it over to Todd. So go ahead and get started.
Great. Thank you so much, Irina. It's really great to be with all of you today. I know we're all making a sprint toward the finish of the calendar year here. Universities, we're busy with grading and things, and normally this is the last week of the year for many of us working. So it's really a pleasure to be here. And Irina, thanks for the opportunity to share some of the work we're doing here at the University of Texas at Dallas. And so, given that many of you are working in the computational mechanics area, I'll be covering some topics from our research related to design. One thing I'll emphasize is the multidisciplinary nature of the design problem. And I'll also be speaking a bit about operations, and there I'll be discussing some of our work in developing digital twins. So, and Irina, thanks so much for mentioning that upcoming meeting conference in September. That looks great. But before diving into any of those technical details, I know too, this is not necessarily a wind energy group. So I want to cover a little bit of background just to kind of set the stage for things. And I want to start with what our high level challenge is for designing a renewable energy generation system. And anytime I start a design problem, the three things I'm primarily thinking about are cost, performance, and reliability. So costs need to be competitive with other generation sources. In order to do that, we need high performance in terms of efficiency of the generation system. And of course, the system needs to be reliable, reliably providing power for its 20 to 30-year design life. And the primary metric that we focus on is the levelized cost of energy, or LCOE. This is dollars per kilowatt hour or cents per kilowatt hour. It's the generation cost of the electricity. And we can think about those cost, performance, and reliability really folding into the terms here on the right-hand side of the equation. We have upfront capital cost, our capital expenditures. In terms of performance, we're focused on AEP, that's the annual energy production over the lifetime of the asset. And then we have operational expenditures over the course of the lifetime of these machines. We'll have some operations and maintenance cost, and that's really where the reliability factor comes in. And so in order to keep the LCOE low and competitive, we need to focus on cost, performance, and reliability. And just to give you kind of an idea of wind farm layouts, here's an example of kind of a typical land-based wind farm in the U.S. This is Sweetwater, Texas. It's a city located about 2 hours drive due west of where I'm at here in Dallas, Texas. And so this is a wind farm. And actually in this image, you can see probably hundreds of wind turbines arranged into this wind farm arrangement. There's also a lot of activity in offshore as well. Many of the early installations have been in Europe. In fact, this is one of the oldest wind farms in the offshore wind farms in the world you're seeing here off the coast of Denmark. This was installed in the early 1990s, maybe 30 years old or so. So offshore wind farm. What you're seeing here is a wind farm that's installed relatively close to the coast. It's just a few miles off the coast, and it's also installed in relatively shallow waters of maybe 5 to 10 meters deep. And that's where really the early offshore wind installations have been, close to the coast and in shallow waters. And that's been done primarily to keep down cost. So most of my presentation today is going to look at research that we're doing related to offshore wind, and just looking at a high level, there are a number of opportunities and challenges for offshore wind. In terms of opportunities, offshore wind is important because these machines, these wind farms, can be placed in relatively close proximity to major population centers that live on the coast. Think East Coast, West Coast. The wind resource is very consistent and strong. There's a lot of space out there, and we're not limited in terms of size. These are truly massive extreme scale machines. We're talking blade lengths of over 120 meters. So the length of a blade is more than the length of a football field. Going offshore has lesser issues in terms of transporting these large components. There are a number of challenges as well, and this is really where a lot of the research has been focused, is addressing the higher costs of offshore. Primarily, these higher costs are due to addition of new costs that don't exist on land, namely the underwater support structures, all the cabling arrays, and just greater complexity in terms of accessing this more harsh environment. Here's a schematic showing kind of an artist rendering of what a offshore wind farm installation would look like. And one thing I want to emphasize here are these two large vessels. These are jack-up vessels. These are ships that can go to port. They can pick up blades, towers, mechanical components, the nacelle. They house a large crane. They move to site, and then they're jacked up. They have these long feet that extend down to the seafloor and then jack up the hull of this vessel. And then the crane, you see the components are installed piece by piece. And so this typical process can take many days or maybe several weeks to install a single machine. And there are a number of machines out on the market today as well. This is truly a global industry. In the US, the top wind turbine supplier is General Electric, GE. Goldwind is a major supplier in China and growing around the world. And then there are two major Danish manufacturers, Vestas and Siemens Gamesa. But these four companies here constitute a really large percentage of the overall market. And yeah, I wanted to comment on siting as well. So where are we seeing the most activity? You know, in terms of siting wind turbines and wind farms, it's kind of like real estate, location, location, location. And so if we start looking at the upper right plot here, we see a graph of wind speed at an elevation above the ground of 80 meters. And that really deep red color is the highest average wind speeds that we see on the map. And it's mostly concentrated in this U.S. Great Plains area. So in the kind of the central and mountain time zone area. And that resource is very strong. There's more ability to capture power there. That's where we've seen, as you might expect, most of the installation in the U.S. over the past 20 years in Texas, Oklahoma, Kansas, Iowa, and many other states in that area. And really, there's a significant growth in New Mexico and Colorado as well in recent years. One of the challenges is transmission. So if we look at sky glow in the lower right, we see an indication of where the major population centers are in the Northeast U.S. and along the West Coast. And so one of the challenges has been, transmission of this power, but also it opens up a lot of interest in offshore wind as well, having power generation much closer to the end user. So I want to mention a few things about the state of Texas as well. There's really a lot of activity in wind energy and has been for the past couple decades. Here in our state, we have over 40 gigawatts of wind capacity. That's about 28% of the U.S. total. Over 200 wind farms, over 20,000 wind turbines distributed around the state, as you see in that lower right image. At the end of the year 2023, 29% of the electricity produced here in the state of Texas was coming from wind power. And we just crossed 30% this year, and an additional 10% from solar power. So we're at about a bit over 40% renewable power here in the state of Texas. And there are a number of other benefits too. You see in the bottom here, landowners and local communities receive lease payments and tax payments as well, and that can account for hundreds of millions of dollars of annual revenues and incomes. And then kind of the last slide here on this introduction, just looking at a few of the industry trends and challenges. I mentioned these are the largest rotating systems in the world. We're looking at towers up to 100 meters in height, blades 110, even up, we're seeing 140-meter blades out there now as well. Cost is a big factor. If you look at military applications or aerospace applications, you're talking maybe hundreds or thousands of dollars per pound, but we really need to do this in wind energy for more like $10 per pound. So it's a real challenge to do that. And then you see an image down here of transporting. Now, that's a 37 meter blade. So just imagine transporting a 70, 80, 100 meter blade. So the rest of this, I'm going to dive into some of the technical work. And the first thing I want to cover is some of the work we've been doing broadly in the area of wind turbine design. And so hopefully by now you've kind of gotten an idea of some of the challenges in terms of going bigger and bigger and, thinking about how we're designing these systems for relatively harsh environments. If we're going offshore, we have to design for the worst conditions that machine might see. It could include maybe a hurricane type wind. If we're on land, we have to design for major storm conditions. A lot of the work that we've done in our group has really been focused on exploring the limits of the technology, especially going bigger and bigger. Years ago, we did a 100 meter blade design at Sandia. Since then, we've gone on to do up to a 250 meter blade design, which is structurally feasible. But no matter what the size of the blade, there are a number of structural design requirements that must be satisfied. And so let's say we're designing a blade and you see kind of a CAD model over here on the left side. When we're designing that blade, we need to check a number of failure modes, including what you see here on the right. Strength check under extreme loads, deflection. We need to make sure the blades do not deflect enough that the blade tip would strike the tower, which is very catastrophic. Fatigue life, these machines must last for their 20 to 30-year design life. Blades are thin-walled structures. We need to check buckling. And these are rotating systems. We need to check dynamics and flutter. We need to make sure that the system is dynamically stable. And so no matter what type of wind turbine design that we're developing at any scale, at any configuration, these are the things we must check. So our primary focus here is, again, developing large rotors and new wind turbine designs within our group here at UT Dallas. And I've broken this slide down showing on the left some different wind turbine concepts for different configurations. And then on the right side, you see what I would call different technologies that could be applied to any of the configurations on the left. And it's really the optimal or best combination of these technologies and configurations that can lead to the best solutions going forward for all the different environments that we're interested in, whether it be on land, shallow water, or even deeper water where we need floating systems. So in terms of the configurations, there are upwind configurations. So imagine the wind is coming from left to right on this page. This is the upwind configuration. The blades are upwind of the tower. We've been exploring downwind configurations where the blades are downwind of the tower. And that has some interesting advantages in terms of the wind typically pushing the blades away from the tower, and that eases some of the tower strike deflection concerns. We've been looking at two-bladed designs, conventional three-bladed designs, and then more recently we've been doing a lot of work on vertical axis wind turbines, the old egg beater design that you see here for deep water floating applications. And then in terms of technical areas, you can kind of think of the right-hand side. These are individual dissertation or thesis topics for graduate students, blade design optimization, structural dynamics. We've been studying how to integrate active load control most cost effectively into designs, digital twins, blade segmentation. I mentioned we did a design for a 250 meter blade. We realized from the get-go such a very large blade would need to be segmented, so we designed it as such. And then we do a lot of testing work on these concepts as well. So if you're interested to read more about some of the scientific challenges of wind energy, there's a series of articles out there called the Grand Challenges articles. And in 2019, the first article in that series was produced, and it outlined three three primary grand challenges. The first being improved understanding of the wind resource and the wind flow within the wind plant. I know there's a lot of great work ongoing in this area at Sandia currently in terms of measurement technologies, but also wind farm, wind plant CFD modeling. And my colleagues here at UT Dallas are also doing a lot of great work in terms of LIDARs for measuring wind plant flows and CFD analysis. The second grand challenge was outlined as addressing the structural and system dynamics of the largest rotating machines in the world. And that's really the one that my research primarily focus on. My students and I, we're aimed at developing cost-effective, reliable systems that can work for the long term. And in doing that, you really need to develop solutions that work across all scales. And that's really what the sketch here shows, starting at the material scale onto the blade scale and then the turbine scale. So ensuring the system is reliable and dynamically stable. And then there was a third grand challenge, is designing and operating wind plants to support and foster grid reliability and resiliency. And we work some in that area too. Our work in the digital twin area really falls into that stage, because once we design and deploy the systems, we also must operate them effectively as well, of course. So there are a number of things that I could cover here, but I decided one interesting topic, perhaps of interest for this group, would be looking at the aeroelastic behavior of wind turbine systems. And with machines growing larger and larger, aeroelastic stability is just becoming a much greater area of interest. And years ago, for smaller blades of 10 to 20 meters in length, dynamic stability was not such, or dynamic instability was not such a big issue. But now that we're going to these extreme scales, this is becoming much, much more of an issue. And you see in the upper right there a video of this galloping bridge. You may recall it's almost 100 years ago now, the Tacoma Bridge failure. This is a wind-induced dynamic instability, and we can have similar type of issues occurring in wind blades. And so if we look in the lower right here on this flow chart, I've listed 4 types of dynamic instabilities that could occur: classical flutter, edgewise vibration, vortex-induced vibration, and then stall flutter. And in gray, these are the instabilities that have been of most concern up to now in wind turbine design. And so those have also been the focus of our research here at UT Dallas, and it's also work that started when I was a Sandia lab staff member. But vortex-induced vibration and stall flutter are becoming more of an issue as well now for parked conditions when the rotor is not rotating. Classical flutter and edgewise vibration, those are issues that can occur when the machines are in operation. And so just looking at some of the current work that's ongoing, here's a case of vortex-induced vibration or standstill vibration. It's been some work from a number of groups. I've noted some recent studies here doing high-fidelity simulations of blades under a number of conditions. And really the focus here is to understand under what conditions this vortex-induced vibration may occur. So the behavior that we're talking about here is actually very similar to the behavior that you're seeing in that video there. You could also think about the classical vortex-induced vibration case of a cylinder in cross-flow. And when you have flow over that cylinder, if you recall the Struhal number, if you're under the right conditions, there's a lock-in can occur, and that cylinder will begin to move or vibrate transverse to the flow. And that's what we're talking about here. Except we have a much more complicated geometry. We have many other variables in play that can lead to excessive vibrations, even in the parked standstill condition. So that's VIV. There's been a lot of work in the edgewise vibration as well. As these blades get longer and longer, they tend to get more slender and slender, and we tend to have more issues in terms of flexibility and vibration in the so-called edgewise direction. That would be in the chordwise direction along the airfoil of the blade. So a lot of our work has been focused on how do we mitigate flutter in large blades in the design process. And so if we just start looking at some scaling laws, so here's an equation, an analytical equation for the frequency of a bending mode of a blade. You have stiffness properties, mass properties, the length of the blade. You have some parameters associated with the mode number, and then we have this alpha as a scaling parameter. And as we upscale the blade, what happens is the frequencies go down as 1 over your scale factor. So if your scale factor is 2, let's say you're doubling the length of the blade, then your frequency will go down by half. And that is indicating how these blades are just getting more and more flexible as they get larger. So that is a bending frequency. We can also look at how the flutter speeds trend as a function of blade length. And what we see here in this plot is the actual flutter speeds are approaching this red line, which is a kind of a normalized flutter speed. This red line is where flutter instability would happen. And so what this graph's indicating is blades are getting larger and larger. We're approaching, more likelihood of that flutter instability. And the way we typically predict these, we'll do an analysis, an aeroelastic analysis, where we're going to start at a low RPM, and then in the analysis, we do modal analysis at different RPM values, and then we're looking at the damping of a set of modes, and we're looking to see when one of those modes may have a damping that begins to drop and eventually goes negative. And if that damping of a mode is negative, that mode could go unstable, and that indicates that mode could be a flutter mode at or above that RPM. That's our analysis procedure. I mentioned earlier the Sandia 100-meter blades are actually a series of 4 of those blades, and in this series, the focus of the work, they're all same length blades, all 100-meter blades, but the focus was on optimizing the blade mass to make that blade as lightweight and low cost as possible. But what happened as we did that, we reduced the flutter speed significantly as we went along. So in all those cases, the flutter speed was still safe, but we were getting even closer and closer to an instability. We did some work here at UT Dallas looking at how could we optimize the structural design to mitigate that. And what we were able to do through careful placement of mass around cross sections, we were able to increase the flutter speed by more than 10%, and at the same time we could reduce the blade mass around 1%. So there are some things that we can do in terms of structural design and airfoils to mitigate flutter. So a lot of our work, as I mentioned before, is focused on new configurations. So I just showed some results for flutter analysis of kind of the traditional 3-bladed upwind design, but we've been looking at 2-bladed designs and vertical axis as well, and that's really a new area for aeroelastic stability analysis. And so we asked some questions. If you were to compare aeroelastic instabilities for 2 versus 3-bladed machines, how might they compare? And ultimately, are there any advantages of two-bladed design over three-bladed design when it comes to aeroelastic stability. And maybe I can kind of spend a little bit of time here illustrating some of the size trends. And so here's the Sandia 100-meter blade. This would be a 13 megawatt machine. The typical machines being installed on land are about the size of these machines here, maybe 60, 70-meter blades. We did a study of two-bladed rotors. Here's actually a series of, these are all 13 megawatt designs, but having a growing rotor diameter, 25 megawatt design. And then here's the 50 megawatt design. So with almost 250 meter blades. And so as I mentioned before, that's structurally possible. We did the detailed design on that scale rotor. But the logistics, the manufacturing, the transportation, and all of those aspects would need further work. You can kind of see the Eiffel Tower here. I mean, the Eiffel Tower is a massive structure, and we're talking designs that are much, much larger. Okay, so back to that question, two-bladed versus three-bladed. And so just quickly, some definitions. So edgewise, this is the chordwise direction. Flapwise is 90 degrees to that. And here's a plot of damping versus RPM based on that analysis procedure I mentioned. And we looked at two types of instabilities, classical flutter and edgewise instability. And you see the typical kind of classical flutter, you have really high damping, and then a sudden drop off. And that's a big concern given how sudden that damping drops off. Edgewise instability, relatively lightly damped to begin with, but eventually that will go negative. So what we found in this study, so we had, of course, designed three-bladed rotors and two-bladed rotors, and we were able to compare all of these. And what we found is that the first instability for the three-bladed rotor was the edgewise instability. That means first means which instability occurs at the lowest RPM. When it comes to the two-bladed designs, it's the classical coupled mode flutter that occurs first. And so one reason for that, when we have these two-bladed rotors, we tend to increase the size of the chords, and that really stiffens the blade up in the edgewise direction, and that tends to push that edgewise stability to a higher RPM. And so, what we've been able to do here, put a number of tools together that we could add to our blade design and optimization tools to more comprehensively study all the design requirements, not just strength, buckling, deflection, and fatigue, but also adding flutter and modal analysis, because when you go to a really large scale rotor, kind of putting our computational mechanics and design hat on, there's so many potential failure modes that just become critical or code red. There's so many different things we have to consider in this design process. All right, so I talked about three-bladed and two-bladed designs, but what about floating vertical axis rotors? And so we've been working on developing a floating vertical axis wind system, or VAT. We just call that a VOT, with support from the DOE ARPA-E. And so here's a case where we're also designing a really large scale system, and we're concerned about the stability of these rotors. And so we ask a number of questions. So what are the typical flutter modes? What's the impact of different design parameters? How about the floating system? How does that impact the design? And so it's a little different here in terms of what types of modes go unstable. For vertical axis wind turbines, it's primarily a tower mode that we're concerned about going unstable, rather than individual blade bending modes. I'm going to speed up a little bit here because I want to get to some of the other topics, but the floating system has a very major impact on boosting the frequency. So if we take a vertical axis rotor on land and we take that same machine and move it offshore, the floating system, by changing that base boundary condition, moves those frequencies higher, and that improves our ability to avoid resonance conditions. This floating system also has a huge impact on improving or increasing the flutter speed. So uh, here's our kind of baseline 5 megawatt design. The nominal rated RPM is 7.8 RPM. So in the higher wind speeds, that's the max RPM that we operate this rotor at for optimal performance. If we were on land, we would predict a flutter speed of around 17.4. So we're safe even on land, but if we move offshore with the floating condition, we get the green curve. And so our damping doesn't go negative, does not go unstable until about 44 RPM. So we're talking 154% increase in the flutter speed. It's really a great result because it gives us some extra margin where we could actually go back and take advantage of that in the design process. I mean, this is one of the results I always get excited about because we're just taking the same design and changing that base boundary condition. It's a big advantage of moving offshore, and we have enough challenges as it is moving offshore. It's nice to have these kind of benefits. So the last thing I'll mention on the design work is, roughly 2 years ago, we did some testing. You see the test team here in the middle, me and a couple of graduate students who've been working on this project and designing this rotor and all the full scale and all that. But we were able to show that, you know, inherent good stability and measured a lot of great data to better understand the interaction of a vertical axis rotor with the floating system. All right, so part two, I want to tell you a little bit about some of the work we're doing in digital twins for wind turbines. And so, this is an area where there are actually a number of definitions out now. This is really an emerging and exciting field. But my definition is digital twin is a numerical model of a real asset or a wind turbine. And it also should be a model that can be periodically updated with new information and new data as it becomes available over the lifetime of the machine. And so we started with a digital twin project to support our WindStar industry consortium. And so the members of this industry consortium, WindStar, and many of them being owner operators who own and operate wind turbines, they have all these machines out in the field, and they love to have models of those machines, such as open fast aero elastic models, so they can do studies to say, well, there's something happening with my machine. My check engine light went off. What's going on? I could really use a model to help me troubleshoot what's going on. Maybe there's an underperformance issue. There's a power underproduction of power. These models, which are the same type of models we use for design, can be used for decision support in wind farm operations. Maybe you've gone out and added a new control system to a machine. Having a model could allow you to evaluate and make sure your new control actions are going to be done safely. When we started working on this, the first thing we realized is how challenging it was to gather data. There's really limited data available to build the type of models that we really want. And so what we focused on for the first year of this project is how can we develop these open fast digital twin models based on limited data. And the basic idea is to start with some baseline reference wind turbine, and then we'll do some adjustment to aerodynamics, blade mass properties, blade stiffness properties, tune the controller, and then we'll have a calibrated digital twin model. And so we're building upon an existing reference model, and then our methodology is basically to scale some of the parameters. So let's take a look at the aerodynamics part first. Let's say that we know the power curve, and that's something that should be readily available as a technical spec or as an owner operator. You can measure your power as a function of wind speed, and so that's your target power. And let's say we start with an initial model before we've just as a starting point, we're at these red dots, and the goal is to adjust the model so that the red dots move over to those light blue target data dots. And in our methodology, we're adjusting the variables that you would adjust in the design process: chord, twist, and lift and drag coefficients. To improve this, we've also added the thrust coefficient as a function of wind speed. So we have, our limited data in this case is a power curve and thrust coefficients. And what that gives us is an ability to get the loads correct in terms of the torque load and the thrust loading on the rotor. And that's really, really important for this overall model to be useful. For the structural model, we need mass properties, blade mass, blade center of gravity, some blade frequencies, and we use all that information to adjust the stiffness and mass properties of the rotor. And so we've shown this approach based on limited data to be very successful. And in fact, the last thing we've done for our WinStar members is develop a graphical user interface that's very user-friendly. User can input all of this target data, and then the output is an open fast model that represents your wind turbine. So that's a product of this work. Something else we worked on is a multi-fidelity digital twin. And so open fast models will typically have some kind of low fidelity aerodynamics and low fidelity structural models. But what if you go out in the field and you have a crack in the blade? Is that blade going to be safe to operate? Let's say we repair the crack. Is the blade safe to operate now under whatever conditions we expect? That's really where a high fidelity model like you see here, a really kind of fully resolved geometry, becomes super valuable. So we put together a methodology that follows the blade throughout its entire lifetime, starting at the design phase to manufacturing, to lab testing or before blades are installed, and all the way into field operation. And so we're gathering data throughout this process. So this really overcomes the limitations I mentioned for the prior case, where we're looking at machines that are already out in the field and we don't have any information about the design, manufacturing, or lab testing. Really, all we have is field operational data. And so here's kind of a flow chart of how we gather all that information throughout its lifetime. And we had an opportunity to demonstrate this process with a blade that we designed a few years ago. I'll show you here on the next slide, but it's actually, it's actually right here. It's a two-bladed design that was tested at the NREL National Wind Technology Center for a few years. But this is a 20% scaled version of a 105-meter blade. So this is a 21 meter blade, and our group here at UT Dallas was responsible for designing the structure for this blade. And so just in general, the multi-fidelity digital twin has really a lot of benefits. Number one, ensuring safety requirements are confirmed using the high fidelity model. In this case, this was a very innovative, highly flexible blade design. We were pushing the margins of performance, developing this digital twin model, starting with our design, following manufacturing. We did testing, we gathered more data. This gave us a lot of confidence when we went into operation that this blade would perform safely. And it's something you can implement for all the major components. I'm showing for a blade, but you can do a multi-fidelity digital twin for drivetrain, tower, any component that you want. I wanted to point out just some of the data that we were able to gather throughout the manufacturing stage. So we designed this blade, but once it went to the composite fabrication shop, there were some changes that happened, some intentional, some not. And so we were able to account for layup extensions, some deviations in terms of the adhesives and overlays, excessive paint, addition of some other components that weren't in our model, like strain gauge wires, balance box, etc. And so ultimately, we had a very accurate model that represented the system. There's another topic here that I think is really important, and and I've intentionally put this kind of in a chronological order, starting with part one was about design, and part two was about operations, and then part three is, well, what do we do at the end of life? And so I want to talk a little about some of the work we've done in sustainable, recyclable materials and manufacturing approaches. And really a lot of our focus here is what might we do even in the design phase so that at the end of the life of a blade, after 20 or 30 years, that blade can be repurposed, recycled, so forth. And so just looking at typical blade materials, this is a typical blade cross-section. The primary load carrying members are these black spark halves. That's going to be unidirectional carbon or glass fiber. You have these shear webs. So that really the primary structure is this box beam. And then at the trailing edge and leading edge, you have sandwich composites that are really designed to just maintain the shape of the airfoil. And I just happen to have a kind of an example here. I don't know if you can see this on camera, but this is a sandwich composite. On the top and bottom surfaces, you have a fiberglass face sheet, and then in between, in this one, you have balsa wood, but it could be foam core or it could be something else. And so there's really a large amount of sandwich composite as highlighted here in a blade structure. So in terms of sustainability and recyclability, these panels are very important. So here's a photo just showing a typical manufacturing of a 75-meter long blade. If you look closely here, you can see a full-size human there, just to get an idea of how big these blades truly are. But the way these blades are made, material is laid up in the mold. You have these two molds, and then you put a bag over it, you infuse resin, you cure it. After it's cured, one of these molds is hinged, and the hinge comes over, and you lay one half on top of the other half. Kind of think of it like a clamshell, but it's really, really major operation, a lot of material input. Typically, blades are made with epoxy or polyester resins, but there's a lot of interest now in thermoplastics for more sustainable, recyclable blades. And so one of the things we've been looking at are not only recyclable resins, but also PLA. So potentially using 3D printing in the blade process. As you know, PLA is one of the really common materials used in 3D printing. So if you look at options in terms of what you do at end of life, you see here a bunch of blade sections that have reached their end of life after 20, 25 years. So what do? Well, there's a lot of work going on looking at how we recover the fibers. Maybe you can grind up these blades and recover the glass fibers. There's been work looking at reuse or repurposing. I really like these two. You've got a bike rack. You see this blade being cut out here and used as a bike rack. You have playground equipment. This is in is in the Netherlands. And then there's a lot of work looking at new materials, including thermoplastic resins and even thermoset resins, including vitrimers that can be recycled based on this new chemistry. So really a lot of exciting work going on there. Kind of our focus has been more on these thermoplastic cores, and really our big interest is in 3D printed core. So I mentioned balsa and foam core, but 3D printing is another great option, we think, for the core material. So one of my studies, or one of my students rather, Dong Yang Cao, did a lot of great work a few years ago studying 3D printed core. This along with some of my colleagues here working in the computational experimental mechanics area, Hongbing Liu and Dong Xian. So we were really interested to know how these 3D printed cores compared to traditional cores, including foam and balsa. And what we found is in terms of strength and modulus, they perform quite well. And you can see all the results there in this composite part B article if you have interest. Thermoplastics also give us a great opportunity for new joining methods. So we studied two joining methods, the first being resistance welding. So you see two yellow blocks here in this schematic. Those are the blocks applying pressure to these blue thermoplastic substrates. And then in between, you have some metal mesh heating elements. So you heat this metal up and it will liquefy or melt the thermoplastic. And then you turn the power off, and when it cools down, you have a joined structure. And so I was really interested to know how does the strength and stiffness of these resistance welded joints looked. And so we fabricated some specimens here at UT Dallas. You see what the interface looks like. You have one polymer and the other polymer being joined here. This one happens to be a white material, 3D printed. Over here you see some black PLA material that's being joined. And then over here on the right, you see the metal mesh that we use. This was a nickel copper, and we found that to be best in terms of performance, in terms of power usage, and so forth. But this technique is very effective. We're able to get to 95% of the properties of the continuous, and that's just kind of initial. I think we can even do better. We also looked at a thermoforming process where there was no metal mesh. So we're just using a heating element to melt the thermoplastic and then join it together with this apparatus we have here that keeps everything aligned. And we have a 4D CT machine here at UTD. We're able to look internally at the bonding quality. And this is something we can do, 3D of a function of time. It was really interesting to see qualitatively, the high quality of this type of bonding approach. All right, so that brings us to the end. Wind energy continues to grow. There's a lot of activity on land and especially a lot of new activity offshore. Our focus has been on developing new solutions for, say, new concepts to really help us do better in terms of cost, performance, and reliability for the offshore environment. And we're really excited about the prospects for digitization and digital twins for wind energy as well. We've studied, ways to overcome the data sharing issues, and there are some ways to do that and develop some new kind of frameworks for multi-fidelity approaches. And I want to just say quickly, big thanks to all the students. We love to get together and socialize. One of our big events is annual pumpkin carving. And so we have a lot of folks from all around the world who are joining our group and our first time pumpkin carvers. But, it's my pleasure to present all this here. But big thanks to all the graduate students and postdocs and collaborators. And thanks to our sponsors as well, and the DOE, ARPA-E, and NSF, and many other places. So, Irina, everyone, thanks so much. Be happy to take some questions.
And this is where we clap, and I just pushed the clap emoticon, so hopefully something is showing up there for you. Excellent talk. Are there any questions? Are there any questions online? So I had a few questions. So you had a slide, the three and the two blade designs, and I just noticed that the largest ones were all two blade. Is that something? I mean, does doing the two blade design or
I'm sorry that I missed part of that. The microphone dropped a little bit for me.
yeah, oh, this slide, yeah, exactly. Yeah, I was curious if the two blade design allows you to make bigger turbines, as the image
Yeah.
suggests.
Yeah, I mean, you can go bigger with three-bladed, but um, our findings from a structural point of view, two-bladed is better.
Mhm.
You're able to grow the chord size, and it solves a lot of the issues you have in the chordwise direction, that edgewise direction, in terms of aeroelastic stability, and it also stiffens the blade up for the gravitational loads. So when you go past a 100-meter blade, the gravitational loads are as significant as the aerodynamic loads. And so you have to account for that. And the two-bladed makes that easier. In fairness, though, the downside is uh, with two-bladed, um, when you yaw the machine and reorient for a changing wind direction, you tend to have a bit more vibration into the tower. And so, rotor design is more favorable at these truly extreme scales, but you probably need a beefier, more costly tower for the two-bladed case.
I see. And I was curious also, can you say a few words about the simulations that you're using for this and their cost? So is it like a DNS or something less expensive or?
Yeah, so we use a lot of different tools, and it's probably won't surprise anyone. A lot. I showed a lot of design work, and in the design stages, we use more kind of low to mid fidelity tools. But then in final checks, we'll go to a higher fidelity CFD approach. And just one of the big challenges is the multidisciplinary nature. I mean, we really need simplified models that capture the floating system, aerodynamics, structures, dynamics, the control system, all of those things together.
Okay, and then I guess last question from me. I was curious if you've started to incorporate any tools from machine, maybe something that isn't really feasible given the limited data.
Yeah, that's a really important topic. I have colleagues here at UT Dallas working on that. Um, that's another way of developing these digital twin models. Our approach has been kind of leaning on these, like I mentioned, open fast. I mean, every people who work in the wind energy field know open fast. It's a wind turbine simulator. You have aerodynamics, structural models, control system. You can simulate, typical kind of wind conditions that you have. You can model the floating system. And so our approach is really to build upon a physical model and adjust model parameters of those models. And that way you have access to all of the capabilities that you would in the design phase. Machine learning models tend to be more black box, right? It's input, output. And so maybe some of the physical intuition you might be losing there, but that could definitely be an area. That's super powerful tools. We should be doing more work in those areas.
There, I had a
Any
really
questions online? I don't
simple
want
question.
to. Oh, go ahead.
I don't know if you can hear me or not.
Yeah, I can hear you.
Okay.
Please. Yeah, go ahead.
So I may have missed this, and it may be obvious, but what's the scaling in terms of power versus the length of the turbine blade, as for example in this figure?
Yeah, that's good. So if you're just doing a geometric upscaling, the power just goes with the swept area. So you see the circles in these plots. So it's just pi r squared, where r is the radius of the rotor.
Okay.
And so if you double the blade length, you should be able to get 4 times as much power, assuming you have the same operating conditions. Now, in this case, you see a series A, B, and C, and they have 104, 123, and 143 meter blades. We purposely upscaled those machines as a way to reduce cost of energy. And for example, this 13A it's really a 13 megawatt machine. The 13C, we could have operated that as maybe a 16, 17, 18 megawatt machine, but we decided to limit the max power to 13 as a way to cap the design loads, and that will help us reduce the cost. And so those are some of the directions that the industry is looking, is putting a longer blade but not operating it at the full potential power rating.
Okay, thank you.
Yeah, thank you.
Other questions? Okay, well, we're a little over time, so I think we can go ahead and wrap it up. This will get posted like the other webinars if you know people who are interested